Okay, in this video we'll look at category 2 methods of assessment methods. And these apply to what we'll call watershed modeling methodologies. Okay, so first to give some definitions, a model is a representation of some system, in our case environmental system, hydrologic and water quality, through the use of some mathematical equations or relationships. Modeling system as a computer program or software package that incorporates the methodology, taking input and then generating output to facilitate some application. In our case, it would be to facilitate the analysis of TMDL to look at where the loads are coming from, implementation of BMP, and seeing what effect the implementation of BMPs will have on what kind of benefits there will be from the implementation of BMP. And so then the application is the use of the model for that purpose, to evaluate some particular situation. So some definitions that are generally used in hydrology. They don't have to be used just in hydrology or water quality, environmental type thing, but I'll use these definitions in basically distinguishing different models from each other. So there's the something that's deterministic, and for that it's something that is known with certainty, or the outcome from some combination of interactions is known with certainty. So you have some equations, the inputs are known into the equations, the parameters in the equations are all known, the output from that known input and known equations will give you an answer. There's no uncertainty about the answer, so it's considered to be deterministic. Probabilistic is something where the inputs or the parameters of the system are not known with certainty, and so then of course the outcome of that will be some uncertainty. So an example would be the toss of a coin. You don't know everything about the dynamics of the toss of the coin. The coin could come down on head, could come down on tail. Stochastic means that it's like probabilistic, except for with stochastic the sequence of events is important, whereas with probabilistic the sequence doesn't matter. So when you look at trying to estimate rainfall, the sequence of rainfall events is important. Whether you have rain every day or not, rain from one day to the next, a stochastic process or stochastic event is one in which the sequence in which those events occurs is important. Whereas for a probabilistic one, you could have any kind of arrangement of individual events occur. It will not affect the outcome. Then mechanistic is something where basically the equations that are used in doing the model are known from the principles of physics, chemistry, and biology. They're known exactly. So an example would be Navier-Stokes equations in fluid mechanics. And mechanistic models are often called white box models. That is, you can see inside of them and see how they're functioning. Whereas an empirical one is often called a black box model. There, basically, the equations are based on some observation. It might be a regression equations, such as what we have in the simple model. So with those definitions, we can classify watershed models into several categories. This was done by Clark in 1967. So models can be mechanistic, that is white box, and deterministic. So inputs, equations are known exactly, parameters are known exactly, outputs got to be known with certainty. Mechanistic probabilistic would be one in which the inputs might be not known with certainty. So rainfall, for instance, is not always known with certainty. It generally isn't known. There's a probabilistic nature to it. So if you don't know the inputs with certainty, even if the equations of the model are known with certainty. The outputs will be uncertain. Same thing with stochastic as applied to a mechanistic model. And then we can apply the same modifiers to empirical models. And again, the empirical models are ones in which the equations are based on observation. It might be regression equations, let's say, and those can, or that model can be driven by deterministic, probabilistic, or stochastic type situations. In addition to what I just talked about there, the classification, we can also make these distinctions for watershed models. The models that are used for TMDL analysis can either be put into a category called lump parameter models, and examples of those are the SWAP model, the HSPF model, and the SWIM model. The SWAP model was developed by USDA. The HSPF model was developed many years ago based on the Stanford Watershed model. HSPF means Hydrologic System Program Fortran. And then the SWIM model was developed by the EPA and is now commercially used for analyses of urban areas. SWAP model is usually used for non-urban areas, agricultural, forestry. HSPF model is used for very large watersheds, such as the 8-digit HUCs here in Minnesota. In contrast, the lump parameter models are distributed parameter models, such as GESA, which is the Gridded Surface Subsurface Hydrologic Analysis model, AGNIPS, which is developed by the USDA. The GESA model was developed by the U.S. Army Corps of Engineers, and SHETRAN, which is developed in Europe by a group of scientists there back in the 1990s. So some example illustrations that show the difference between lump parameter models and distributed parameter models. Lump parameter model might be this. We take a watershed, we subdivide the watershed up into sub-areas, and within each of the sub-areas, basically everything is treated as being uniform. So the different colored areas that you see there probably have some variability in characteristics within each of those different colored areas, but the parameters that are used for each of the different colored areas are constant, or they're uniform. And so we don't distinguish things changing conditions within any one of those sub-areas. The runoff and pollutant load from each of those sub-areas is routed downstream along the stream channel. You can see the blue line is the stream channel. And so you have discharge and contaminant or pollutant loads coming out. And here we have flow versus time graphed for each of the sub-areas, and then through the routing of all the flow downstream, we end up with a hydrograph at the outlet, and also pollutant load at the outlet. So with this kind of model, we can analyze what's happening within each of the sub-areas, but we don't have distinction exactly the details of what's going on in each of the sub-areas. But this is better than actually just trying to quantify what's going on at the very outlet of this watershed, because if all we did was measure flow and concentration at the outlet of the watershed, we would not be able to determine where loads are coming from within the watershed. At least with this lump parameter model, we've subdivided the watershed into small enough areas that we can at least start to distinguish where loads are coming from. A distributed parameter model like the GESA model, which is represented here, this is for a watershed where the watershed is broken up or subdivided into many small squares, and governing equations for conservation of mass and momentum, and also for solute transport, are applied to each of the squares, and those are combined together in a numerical model to be able to route flow from up in the watershed to the outlet. And we can see here the concentration of, well, basically it's a plot of the water depth at different parts in the watershed. And you got the upland areas, which have very small water depth, And then the blue areas that show up are the depths of flow in the stream channel. And we can also look at solute transport with this model. The Geisha model, as an example, is being used by the DNR to evaluate what's going on at very small scales. So you can actually look here on the scale of 1 square meter in a watershed, whereas you can't do that with a lump parameter model. So lumped versus distributed parameter models just give an idea of the level of detail that you have, and here it's for this table is to evaluate or to get an idea as to what goes on as far as runoff calculation is concerned. So a generalized model, which would be, let's say, might even be something I would have put into category 1 type assessment method. The mid-level model might be one that's more of a lump parameter model. The equation here, CN, refers to the curve number method for estimating runoff, whereas the generalized method just basically takes rainfall amount from an empirical relationship and calculates runoff from that rainfall amount. Whereas for a very detailed model like the Geisha model, you'd use some sort of an infiltration equation at the very small scale to calculate the runoff amount. The assumptions for each of these models is listed on the right side of the table. If you want to look at other details here, we can look at here how each of the characteristics of a watershed and the variables of interest are represented in models that are generalized, very crude, like I say, maybe methods that even apply to category 1 methods like the simple model. Mid-level would be more of the lump parameter type model, and detail would be something more like the gridded distributed parameter model like Geisha. So you can take any one of these, for instance, for pollutant load or pollutants, the very generalized model is going to treat everything uniformly. You'll come up with an estimate for the whole area, not any kind of breakdown based on sub-areas. Whereas the mid-level would have multiple areas of sources of the pollutants, and you'd be able to estimate the loads from each of those sub-areas. But again, the sub-areas may be fairly large, so you wouldn't be able to break things down any further with the lump parameter model. Whereas the detailed model looks at very detailed reactions with a chemical and can get you information at the very small scale. So what do we consider when we tried to select a model for our watershed application? Because there's a lot of things to look at here. And the questions are, first, will the model that you're going to choose answer the things that you want to have? So if what you want to have is very detailed information about where pollutants might be coming from in a watershed, you're going to need to use a detailed distributed parameter model. If that's not what's of interest, if you want to get a first estimate of what's going on in a watershed, you might be able to get away with a very generalized or lump parameter model. Another consideration here is whether or not the model has been accepted by practitioners, by the scientific community, and very important here that stakeholders also accept the basis for the model. And of course, to gain that credibility, usually the model has to have a lot of testing and application to make sure that people feel comfortable with it. The model certainly should be simple to use or easy to use by the user. And sometimes models that are very complicated are developed by a single user, and then nobody else ever actually uses it because it's so difficult to use. And as an example of a model that gets a lot of use, the SWAP model is used by about 150,000 people around the globe. That's an indication of how simple the model is to use. Still takes some work, but it works very well with ArcGIS and map window GIS, and having that kind of capability to provide inputs to the model is a big plus. The Geisha model also has some of those same capabilities, but it's much more difficult to use, and it also requires a great amount of computing time. Really important here is whether or not you have data that are appropriate to use the model. If you don't have the data, then you might just well be shooting in the dark as far as trying to estimate what's going on. And then, will the model show effect of changes in land use? If you use a particular model to look at current conditions and then you change the land use and the model doesn't show any sensitivity to that, that's probably not realistic. Such a model has to show that kind of benefit to illustrate or to demonstrate the benefits of land use changes. So here's a partial list of some of the data that's required. I'm just going to list those. So weather data, soil type, groundwater, aquifer characteristic, land surface elevation, vegetative cover, stream channel network and channel cross sections, locations and characteristics of hydraulic structures, soil erosion characteristics. And there could be other items that you put in there also. If you're looking at chemical like nitrate, then you probably need to know how manure and nitrogen fertilizers being applied across the landscape. That would be very important. The things I've listed here are all have to do with the hydrology itself. So if you want to look at chemicals like phosphorus, nitrogen, if you want to look at heavy metals or anything like that, you need to have that kind of information to run the model, come up with anything that is meaningful. So steps involved in selection and application. Well, you need to look at the objectives of the analysis. What do you want to be able to accomplish? You need to look at what you really want to answer. For instance, do you want to look at the effect of land use change on daily solute concentrations? Or are you more interested in the effect of land use change on annual loads? Because two different models, you would probably select different models for doing those two different objectives. You want to select a model that will address your questions. You need to set up the model, you need to test its performance. That requires that maybe if you have some data, you want to calibrate the model for that particular situation, and then you want to verify that the results that you're getting are realistic. You then apply the model, interpret the results. You update the model to include any new information that might come along with time. All right, so this shows a list of the available models at the time when this presentation was put together a long time ago. There would be other models that are available, but the ones that are most interest to us that are used for TMDL analysis are listed here. There are other models here that are not used in Minnesota or even in most of the United States for that purpose. So here on this list, we have the Geisha model that's listed, the Basins model, which is an EPA model, which includes several different types of submodels. HSPF model is listed here. And the type characteristic of each model, whether it's a grid-based model, whether it's a lump parameter model, is shown here. The time step in the model, whether it's a daily, monthly, annual type of time step that's used, the kind of hydrology, surface water hydrology, surface water and groundwater hydrology, what kind of water quality characteristics can be analyzed with the model, and the types of BMPs that were implemented in the models at the time when this table was put together. So, for instance, with the Geisha model, it's able to look at daily time steps on the order of 1 second. It's a grid-based model. It does very detailed stream channel flow. It uses the mechanics equations, so basically it's very fundamental in the equations that it used for doing calculations. It does both surface water and groundwater flow processes. It'll look at water quality. This table says that it does just sediment, but actually it's being improved so that it will include nutrients as well. So it does have a general pollutant transport component to it. And you can use it to look at things such as vegetative buffers, wetlands, for BMPs, different kinds of vegetative practices. And this is just a continuation. It has some other models like SWAT model, SheTran, so forth. These are some of the water quality results, the outcomes or the results that you would get out of one of these, any one of these types of models. And this is not the complete set of models, so some of these are the ones that are most used for TMDL analysis: AgNIPS, HSPF, and the SWAT model. SWIM is used, SWMM is used more for urban or suburban areas, but you can see that these models do provide many of the water quality parameters that are of interest. The HSPF model, for instance, does output for most of these parameters that are of interest. SWAT does that, but does it more on a daily time step, whereas HSPF does it on an hourly time step. Okay. Again, here are some different features that can be represented in these models. The amount of time that's required to use a model, the experience that's required, how much support is available. Can you call somebody up and find out if the model is not working very well? Can you call somebody up and get some help with it? What kind of data needs are required? And whether or not there's a cost to using the model is all listed in this table. And this again would be for many of the different models that I've just referred to. Okay, so with that, I'm going to go on and look at other assessment methods. Those other assessment methods include biological, geomorphic, and geochemical. But I'm going to stop the video here, and I'll make a third video to cover these other methods.